This is part 2 of the Module 7 lecture. And here in this section, we're going to talk about the sampling distribution of the mean, which corresponds to section 7.2, 7.3, and 7.4 of the textbook. All right, we're going to continue with that simulation that we talked about in the previous recording, where we talked about the sampling error. So now in here, we're going to do exactly the same simulation, except now that instead of doing this 10 times, we're going to do it 100 times. So we're going to roll the die 5 times, calculate the average, and then roll it 5 times again, calculate the second average, and we're going to repeat that process 100 times. So we will end up with 100 averages of 5 rolls. And then we're going to plot the histogram of those 100 averages. All right, if we could do that physically, then we will have something like this. So in here I have the probability distribution, or rather the population probability distribution of the 6-sided die with its mean and standard deviation, and the probability only occur at the integer values. But now if you look at the distribution of the averages of these samples of 5 rolls, then you see that we have this histogram, and then we see also that the averages of these samples of 5 rolls, now they have values that are not only integer, now they have values all over the continuum between 1 and 6. Not only that, if you look at the standard, the mean of these 100 averages, you see that the mean of those is 3.509, and a standard deviation of these averages here of 0.742. And you see that the mean of all these averages, the 3.09 is pretty close to the population mean, but not the standard deviation of the averages. This is much smaller than the standard deviation of the population. So based on this, we can say that the rolls of the die, in other words, the way we roll the dice, we generate independent outcomes. This is very important, because as long as we have independent outcomes, we have these characteristics. And also the population mean, as we said, and the mean of the distribution of averages are approximately equal. And the standard deviation of the distribution of averages is smaller than the population standard deviation. And finally, the sample averages are values now of a continuous random variable with an approximately symmetric and bell-shaped distribution. That's what we could see from just 100 averages. So in fact, this distribution of samples of 5 roll is an example of a sampling distribution of the mean. Here we created it through a simulation. And we have sampling distributions for every statistic you can think of, such as the standard deviation and the population proportion. And conceptually, you would construct a sampling distribution just as we did with the die. You will take a random sample of certain sample of the same size, calculate the sample statistic, and compute and do this many times so that you can compute the probabilities for each interval of values of the statistic. And I'm saying intervals because now the random variable is the averages, and now it becomes a continuous random variable. Now, this way of constructing the sampling distribution is not necessary, because sampling distribution have very specific characteristics that do not require this brute force approach to construct. And what we're going to focus on is on the sampling distribution of the mean only. Later on, we'll talk about the sampling distribution of the proportion, and much later in the course, we'll talk about the sampling distribution of the standard deviation. All right, so if we have samples of equal size drawn independently from the same population, then the sampling distribution of the random variable mean, the sample mean, and I'm using capital X because now the average becomes a random variable. And that random variable, or that sampling distribution for that random variable of averages, is exactly the same as the population mean. And the standard deviation of the sampling distribution is just the population standard deviation divided by the square root of the sample size. So we don't need to construct this sampling distribution. From the fact that we have independent observations in each sample, and theoretically it can be shown that the mean of the sampling distribution of the mean is just the mean of the population, and that the standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of the sample size of those averages. So now we know two important characteristics. If you remember in chapter 6, when we talk about the normal distribution, it was fully determined by its mean and its standard deviation. So now we have two characteristics of the sampling distribution, its mean and standard deviation. The next question is, well, if we wanted to compute probabilities, what would the probability distribution be of this sampling distribution? And in here, I'm summarizing the results. Now, the theoretical results, not those from the simulation, where we have the probability, the population probability distribution of the six-sided die, and the sampling distribution of means of 5. Now, I don't need to simulate it. I know from the fact that each outcome, when I roll the die, is independent of the other outcomes. Just from that fact, and because I'm taking averages, then I know that the population of the mean, the population mean of the sampling distribution is just the mean of the population mean, and the standard deviation of the sampling distribution is just the standard deviation of the population distribution divided by the square root of the sample 5, of the sample size, which here is 5, and that's 0.7638. And if you look at this 0.7638 and we go back to that histogram, you see that this standard deviation from 100 averages is pretty close. And well, both of these are pretty close to what would be expected from the theoretical sampling distribution. So now we have two important characteristics of the sampling distribution. We know its mean and we know its standard deviation. And here I'm showing a hint that the distribution, the sampling distribution, might be normal. And to determine that, we're going to look at a very important theorem in statistics. It's so important that it's called the central theorem and is the limit theorem, because as distributions, as sample sizes increases, they approach what is called the limit distribution, which is the normal distribution. So as the sample size increases to a sufficiently large number, the sampling distribution of the mean becomes approximately normally distributed. And we have two very important conditions. Very important because as we solve problems, we need to validate this, that in fact the sampling distribution is normal. So number one, if we know, for whatever reason, that the population probability distribution is normal, then the sampling distribution of the mean is normal, independent of what sample size is used. Now, if the population probability distribution is not normal or its shape is not known, well, the sampling distribution of the mean will become or will be approximately normal as long as the sample size is 30 or more. So this is very important, because once we see that we have 30 observations, samples of 30 observations, so more, then we can safely assume that the sampling distribution is normal. And I illustrate these 2 points graphically here. So here, the population probability distribution is normal. And then if we take a sampling distribution of means of sample size 5, that distribution will be normal. If we construct the sampling distribution of the mean for sample sizes of 30 is normal. So regardless of the sample size, the sampling distribution is always normal. Now, if the population distribution is not normal, it looks skewed like it does here. So as you, for example, if you take construct a sampling distribution with sample size, with using samples of size 5, you can still see a hint of skewness. Even when you use samples of size 15, you still see a slight skewness. But if you have reached the point where you have samples of size 30, then you start seeing that this distribution is pretty much normally distributed. So in general, we're going to use this rule that if the sample size is 30 or larger, the sampling distribution of the mean will be assumed to be normal. This is very important because as we solve problems and we want to calculate probabilities using the normal distribution, we need to ensure that the sampling distribution is normal. And again, if we are told the population distribution is normal, well, there is no problem. We don't worry about what sample size we're dealing with. However, if we don't know what the size or what the shape of the population distribution is, well, as long as we have a sample size of 30 or more, then we can safely assume that the sampling distribution is normal. All right, so let's say that we want to compute probabilities using the sampling distribution. Well, we will do exactly what we did in chapter 6. We're going to use table 4 to find probabilities from a standard normal distribution. However, in order to change an average into a z-score, well, we need to redefine how we calculate the z-score, because this is the original formula that we saw in chapter 6. So it's the mean minus the population mean divided by the standard deviation. But now we're dealing with the sampling distribution. So the mean of the sampling distribution is mu x bar, and the standard deviation is sigma x bar. But we know that the mean of the sampling distribution is the same as the mean of the population, and the standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of n. Once we transform that average into a z-score, then we go into table 4 and find probabilities just as we learned to do in module 6. All right, I'm going to stop here. In the next section, we're going to solve some problems or calculate probabilities using the sampling distribution of the mean.